Alright, well, hopefully we can divert your attention from your dinner for just a little bit. I'd like to first begin by thanking SNAME and thanking all of you for putting on our student papers night every year and allowing me to present. Hopefully we won't put you to sleep, and we have a lot of presentations to go ahead. So with that, I'll begin. As you can see, also a disclaimer, because of our schedule at Webb, we start a little bit later because to get our internships in during the winter. We're about halfway through our semester, so I'm almost done with this thesis. So the conclusions aren't quite there, but I have some results, and I'll show you, and I'll talk about it when I get there. So bear with me, but it should be good. So to begin, as you can see, my thesis is on modeling a renewable energy storage system in MatLab and Simulink, and I'd like to thank my principal advisor at Webb, who is our dean, Mr. Matthew Warner. Perfect. All right, to begin, an outline of what I'll be covering. First, I'll cover the objectives of my thesis. I have 3 of them. Then go into the background of why I'm modeling renewable energy and energy storage and the research that's supporting my thesis. Then cover the testing matrix that I applied and are in the process of applying in order to get my simulation results. And then show you some of those early results that I have, try to describe their meaning, and then go over a review of what I've done so far and what we've accomplished and give some recommendations for future work. Again, my objectives, I have 3 of them. The first is to develop a functional model of renewable energy storage system. So that means on the computer I'm attempting to simulate a renewable energy source, so in this case a wind turbine, and then an energy storage system where we can store some of that energy and then redeploy it as necessary. So I'm on the computer, as I'll describe in a bit, using MatLab and Simulink, developing a model which can accurately cover the dynamics of that. My second objective, a little more dramatic if you will, to increase Webb Institute's exposure to simulation resources. So currently we're trying to expound upon our usage of MatLab at the university, and then use Simulink as well to increase our simulation capabilities for future research and educational purposes. And my third objective is to make a preliminary determination from the results that I've obtained in my model of which energy storage method. I'm modeling 5 of them, and I'll describe them in a little bit. Describe which of these is feasible today, if any of them are. And then as a corollary to that, if none of them, or if only some of them are feasible today, what aspects of technology or cost reductions need to change in order to make them more feasible and bring them into the market. All right, so some background on my actual work. Renewable energy storage, or renewable energy sources are mostly intermittent. So the most common ones that we have nowadays, that I'm sure most of you are familiar with, are wind turbines and solar energy. So whether that be photovoltaics or solar thermal, etc. In addition to those, ocean energy, whether it be by waves or tidal or currents, can also be very periodic. So all 3 of these methods, these energy sources, are not constant, reliable sources of energy. They're very intermittent. In the case of ocean, we can attempt to predict, and with tides, it's very easy to predict. But even if it's periodic, it doesn't necessarily match what we need. So even though we can harvest renewable energy, we don't always have the energy we need when we need it, or sometimes we have too much when we don't need it. And so that's essentially a waste on both sides. So a description of how to solve that, or at least what the description is that we're trying to do here with my thesis, is called energy arbitrage. As it's defined here, energy arbitrage is storing energy when the price or demand for that energy is low, and then discharging or selling that energy back to consumers when the price or demand for it is high. Similarly related are the concepts of load leveling and peak shaving, where load leveling is matching our supply profile with the demand profile, and peak shaving is simply supplying peak energy, whether it be from peaking reactors or peaking plants, or in my case, energy storage. But I think I can better describe this with a graphic here. Hopefully everyone can see. It might be difficult for those in the back, but I'll attempt to describe it as best I can. Here in this graphic, the yellow line, the yellow almost sinusoidal curve, is a nominal demand profile. So this would be the demand on the electrical grid or energy grid of what people need at any given point over the course of a period of time. So in this case, they describe it from 0 to 24 hours, the course of the day. The gray bar at the bottom is baseload generation, so that's constantly going. Those are your nuclear plants or well-established coal plants providing that power. But then of interest is the blue section in the middle, this blue, very spiky variable section. That represents a nominal renewable energy source. So perhaps a wind turbine, which I'll be modeling. As you can see, and what would make sense, it doesn't really match our demand curve, our demand profile. It's very variable, it's not very predictable, and though it might be periodic, it's doesn't always have the same amplitude or periodicity, frequency, so it doesn't really help us. It helps us when we can fit it underneath the demand curve, but then in cases over here, for example, we have too much. It's essentially wasted. Or in cases where we're underneath the curve, we can't produce enough. So what we can do with the concept of energy arbitrage, and what my thesis is trying to model with energy storage, is to take all of that wasted energy that we would have from our renewable energy source, our wind turbine, when demand is too low, and shift it so that we save it, and then move it into the empty area to make up the difference with our demand profile at a later point in time. Hopefully that makes sense to everyone. But we can do this with energy storage. And so energy storage can take a number of forms, which I'll describe in a bit, but this is the foundation of what my reasoning is trying to get at. And by doing so, the goal is to hopefully provide a means of increasing the ability of renewables, primarily periodic ones, such as wind turbines or photovoltaics, to more easily penetrate the market sector. We can get a net more amounts of energy, net larger amount of energy out of the renewable source, and so it can make it more cost effective for implementing it in the grid with energy storage. So the second part of my background is going over the simulation theory. As I described, I'm using a software called Simulink, which is an environment within MatLab. Hopefully most of you are familiar with MatLab, or at least know what it is. It's a modeling programming environment, like basically a really fancy calculator. But Simulink itself is a visual programming environment which connects blocks, and each of these blocks represent some object or some mathematical equation, and connects them with signals. And I'll show you a picture of it in just a minute. Now Simulink can solve some complex equations. So every time you connect your blocks together, and each of these blocks have equations, you can create a long chain of rather complex equations and differential equations, which would be nigh and impossible to solve by hand. But with numerical methods and simulation software, we can solve it and produce some results, especially in the time domain, where it can be rather difficult. But what's more critical, especially in Simulink, is your choice of solver, especially when you're using, when you have equations with differential equations. Which solver method that you choose. There are a number of different algorithms that beyond the scope of this you need to know about, but choosing the right one creates the most efficient simulation. And as part of my thesis and part of developing this resource for Webb Institute, we're using Simulink. Identifying the correct solvers to the correct situation is an important aspect. Alright, so with that background, this might be relatively difficult, but I'll try to block it out. I can also zoom in if need be. But this is roughly what a Simulink model looks like. So you can see we have all of these nice little boxes. Each of these boxes represents a physical thing or a set of equations. So we have switches, we have diodes, we have relays. These are scopes like oscilloscopes and whatnot. And then a battery in there, where the battery is a nominal storage system. This is the model that I've been using to actually simulate what I'm getting at, which is a storage system and renewable energy resource. So this chunk of blocks over here, connected by signals, is collectively my energy storage section, which you can see is nominally represented by a battery with my custom design decided curves. This section over here represents a wind turbine, so I'm modeling the power that you can get out of wind at a certain speed, and then converting it with some equations and a nominal DC generator so I can get electricity out of it. And down here is what I describe as the grid load. So this represents a variable load over time that is periodic, but not very easily fixable, so it's very spiky. And that would represent a nice complex load that would have to be matched by my energy storage system. So with that model, I'll describe the matrix that I'm testing. So like I said, I've been describing all of this energy storage, but I can now tell you what energy storage actually is. I'm modeling 5 different energy storage techniques. I'll describe each one of these. These are the 5 here. The names are kind of long because I have stuff with acronyms. It's not too keen that you know what they are, but I'll go over them nonetheless. PHES is pumped hydroelectric storage, so that is taking water and pumping it up a hill essentially, and then to save your energy, and then when you want the energy back, you run it back down the hill like you would in a dam in a hydroelectric plant. Second one, CAES, is compressed air energy storage. So in that case, you're now taking your excess energy and using it to compress air and storing it in tanks, or more commonly in large underground depleted caverns. And then pumping up the pressure on the air, and then you need the energy back. You pull the pressure out from wherever you've stored it, and either run an air turbine with it, or more commonly run it into a natural gas plant to increase the efficiency of the natural gas plant. The third one there, CH2, is compressed hydrogen. In this case, we take our excess energy, we electrolyze hydrogen from common seawater to then capture the hydrogen and oxygen that we get from it, We store the oxygen and hydrogen in tanks, and then when we need the energy back, we take the hydrogen and oxygen, put it through a fuel cell, and then we can produce our electricity directly. The fourth one, VRB, vanadium redox flow batteries. It's essentially a battery except where your electrolytes are separated and are fluids, so you can control the amount of them and pump them against each other to produce your electricity. And the fifth one is simply lithium-ion batteries. Most of you should be familiar with lithium-ion batteries in your phones, they're now in cars. They've become a very common and prolific sort of battery as far as the technology is concerned. Even though it's just a solid-state battery and its sizes and costs can be a little questionable, but since it's so common, I included it in my testing matrix. What I'd like to point out of note of these energy storage systems, though, is in the middle column there, I have coupled power and energy. So most of them do not have coupled power and energy systems, but lithium-ion batteries do. What that means is that the amount of energy that can be stored in the system is not related to the amount of power that you can get out of the system. So in the first four cases, the amount of energy that you can store in a system is simply dictated by the size of your tanks, essentially. The size of the reservoir of water for PHES, the size of your air tanks or hydrogen tanks for the middle two, or the size of your electrolyte reservoir for redox flow batteries. However, in lithium-ion batteries, the size of that electrolyte, since it's a solid-state battery, is directly related to the power. So if you add more electrolyte, you also increase the size of the stack, which then changes your power. Whereas in the first four, your power is simply dictated by your power generating mechanism, usually a fuel cell or the turbine. So in that case, it's useful, and what I've determined through a key aspect of this, it's most useful to have your energy storage system for large-scale applications like this one, to have decoupled power and energy characteristics. So you can simply increase the amount of energy you need with a constant amount of power for a certain area, certain demand in an area. Additionally, I've put on the power and energy costs. So since most of these are decoupled, or in the case of lithium-ion, they're related, the power and energy cost of each kilowatt or kilowatt hour of each system is included. Mainly what I want you to take away from that is that, one, they're highly variable, and most of these technologies are still being researched or attempting to be applied to actual commercial or industrial cases, so their prices are generally high, and ultimately, as I'll show in a bit, it's the prices that are preventing their feasibility and preventing their implementation into the grid right now. But, of note, the energy cost of these first four systems is very low, which means we can increase the amount of energy that we can store in them without having to increase the power cost, whereas in the case of lithium-ion batteries, if we wanted to get more energy out of it, it would be a large investment. So the sensitivities are different each. So with that testing matrix, I'll be applying data that describes each of those energy storage systems into the model that I showed you earlier. As I described at the beginning, the thesis is still ongoing. So I'm currently in the process of running those simulations, but what I currently have now are some early simulation results. So this is me having completed the model, and it's testing it, verifying and validating the model that it works correctly. So what I'd like to point out with this is a time domain result from my simulation. So this is currently from 0 to 8,000 seconds, about 2.5 hours roughly. What I'd like to point out is that in each section, which is periodic, our top graph here represents the state of charge of my energy storage system. So the state of charge, you can see, increases with charging, and then decreases, then increases again, then decreases. So my energy storage system is appropriately charging and discharging when needed over the grid. And then the current and voltage being applied to the load is both periodic and relates directly to the state of charge. So it's correctly discharging the certain amount of energy that it has until it has nothing left, and then charges and discharges again. And you can see that each of these sections is very variable, which describes variable load. Additionally, you can see this discharge curve is different from this one, which has to do with the fact that there's a variable input. So the amount of energy that I'm putting into the system is also varying, and so the amount that I can store with these two different curves, they're slightly different, and the amount that I can get out changes a little bit as a result of my input. Nonetheless, this simulation, it works, it models all of the components according to what I've intended, and like I said, I'm in the process of running the results on each of those 5 storage methods, and in the near future, we'll have those actual results. So as a description of that, as a review of that, these are the objectives I described at the beginning. I've developed a functional model, so that works, which we've just reviewed. And then, as a result, in the process of producing that functional model, I've increased Webb simulation resources, and I'm now in the process of determining which storage method is viable. From the testing matrix that I described that shows the different price points, I'll be evaluating those price points for the amount of energy that each one effectively puts into the grid compared to each other, and then using those numbers, run present value analysis to determine which one would be viable and if it could be applied nowadays. From preliminary results I have now, it seems that only pumped hydroelectric storage is viable, but only by a small margin, which makes sense. It's the only system that's currently deployed today, well, in large numbers. And the other systems are not quite viable, and of varying degrees. You see, when I finish my simulation, I'll become apparent, and if any of you want to read my thesis when you're done, because I'm sure everyone likes reading research, you can find out the answer to that. So I've determined some recommendations for future work already. The first would be to increase the model detail, so that could include more accurately modeling the dynamics between the different parts of the energy storage system and between the connections that relate to it. So maybe modeling some of the fluid dynamics that have to do with pumped hydro or compressed air and hydrogen, something like that. A second recommendation is to convert what is currently a DC system into a three-phase AC system. So that would obviously more accurately represent what's currently in use on the grid today with our AC three-phase power. A third would be to perform a more detailed sensitivity analysis, so quantitatively describe which parts of each energy storage system, whether they be the operating costs, the initial capital costs, materials, production, which aspect of each energy storage system has the most effect on making them feasible or not feasible today. Or the final one that I've come up with is to adjust the simulation for other types of energy storage. So currently I'm using a wind turbine because the wind turbine is directly applicable today. It's becoming very common, but you can also apply to photovoltaics or other types of solar plants or even other types of renewable energy storage systems, renewable energy systems like ocean, waves, etc. Any type of periodic system. All right, and with that, I will take any questions that you have in today's presentation. Yes,
Spenser, can you go back to that table you had of the net kilowatt hour costs? Yeah. I'm looking at that far right column, energy cost. And I'm seeing that the lowest cost is $2 a kilowatt hour.
Yes.
And even on Long Island, which has an outrageously high price for electricity, I'm paying less than 20 cents a kilowatt hour.
Yes.
Looks like you have a marketability problem.
This is true, and like I said, this is largely why none of these systems currently exist. Right now, only pumped hydroelectric storage actually exists in any meaningful way. The data that I have, the research that I have described it as $12 a kilowatt hour, but that's using the modern installation, the modern siting. Both the first two here are both largely dependent on geographic area because you need a large amount of space and large volumes in order to make it effective. So that's given that. That being said, yes, you make a good point that even our cheapest system is still multiple times. Yes, a large amount, yeah. But yeah, like I said, we have a ways to go to make energy storage viable on a large scale. Any other questions? Yes?
Did you consider centrifugal storage?
Yeah, so in my research leading up into the actual simulation, flywheels are very commonly used for energy storage. The issue, or at least the difference that I had, is very few, if any, of those installations are used for energy arbitrage. So that is, moving the excess energy that would produce into areas of deficit. They're most commonly used in small cases to help regulate frequency and voltage on grids. So, like a common, or at least one of the easy ways to describe that is, I know in electrical subway systems and train systems, when you accelerate a train, that puts a sudden load on your supply, and that can drastically change your frequency depending on your control. So flywheels and centrifugal storage that way can help make up that difference to keep your frequency controlled. But in that situation, then flywheels are much better used for high power, short discharge time applications. Whereas what I'm looking at is much longer discharge times over the fixed power on the order of hours or days as opposed to seconds or minutes. I mean, they are viable, they do work. It's a lot of flywheels actually in use right now, but they're just for a different use case than what I consider.
I have one question.
what kind of efficiencies do you have for storing and then recovering?
Well, these efficiencies right here are round-trip efficiencies that are, again, from data that I've collected from other sources. Yeah, it'll be difficult for you to read them back, if you're keen. Yeah, that's okay. Zoom in on that there. Using that. Yeah, so these some efficiencies, they are relatively high. And unfortunately, there's a lot of different literature, not a lot, but some literature that describes these different systems, and a lot of them have differing values for efficiency. These are mostly median values of what I've discovered and what I've read about. At least in these two cases, your efficiency is largely governed by the efficiency of your turbines and pumps, which they say can be relatively high recently. I mean, so pump technology has gotten decently good, especially in reversible flow ones. Batteries, relatively high efficiency, at least in the round trip during their cycle lifetime. Obviously, batteries have a limited cycle lifetime, which is another aspect that I've considered on their use case, which also is why they're so expensive. And then hydrogen in the middle there. Hydrogen is, it's exotic and it's still a long ways off. And fuel cells, depending on which fuel cell you use, you get widely varying efficiency. Your electrolyzer has a widely varying efficiency, so it largely makes sense why it's the lowest.
I guess the hydrogen would be where.
Yeah, like I said, this is from data that I've collected, so I mean, I agree. It's surprisingly, I was surprised that they said that it was about 50%. But yes, and make a valid point.
Very good. Any comments? Any further questions?
All right, well, thank you very much.